Nuclear sizes can be measured very precisely, typically to an uncertainty of a few tenths to a few hundredths of a femtometer, using methods like electron scattering and muonic atom spectroscopy. Think of a nucleus as a tiny ball that scientists probe to learn how big it is. In electron scattering, a beam of electrons bounces off the nucleus, and the pattern of scattering tells us the size, and in muonic atoms, a heavy muon orbits very close to the nucleus, so its energy levels shift in ways that depend on the nuclear radius. These experiments measure lengths on the scale of 1/4,000,000th of a meter, called a femtometer, and repeated measurements combine to give uncertainties that can be as small as a few hundredths of a femtometer for some nuclei. The exact precision depends on the nucleus, the experimental technique, and how well we can control and understand things like electromagnetic effects and the internal distribution of protons and neutrons. Combining different methods and careful theory lets physicists quote radii with very small error bars compared with the size of the nucleus. A common misconception is thinking all methods give identical radii, but different probes can be sensitive to slightly different distributions and require careful theoretical interpretation, so compare consistent definitions and corrections. Another mistake is assuming the quoted precision is the same as absolute accuracy, because systematic uncertainties in theory or experimental setup can shift results, so always check how error bars were estimated and what assumptions were used. Some students believe the nucleus is a hard sphere with a single sharp radius, but in reality, the charge and matter distributions are diffuse, so use models that describe distributions rather than a single fixed boundary. For more videos and resources on how nuclear sizes are measured and what the numbers mean, check out www.gumballdegree.com.